Good afternoon, student of the course 4006. And today we're going to be talking a little bit about Simpson's truncation error and its application to numerical integration. And I have this table here, table 21.2, and this table comes from the book of Numerical Method in Engineering. And this is by Chapra. All right, this is the 7th edition, I believe. And so what I'm showing here is just a summary of the many integration methods that are available to do, when the integral becomes very difficult to do it analytically. You can definitely go through one of these methods and see which one will fit the bill. Like, for example, if you want to apply only one-time trapezoidal rule, that will be evaluation at the low limit and the high limit, and as simple as that, that will generate a truncation error as shown here by only one application. And likewise here, Chapra is showing Simpson one-third rule, the application of one-time Simpson rule, which required 3 points. The point at the lower limit, the point at the middle, and the point at the upper limit. That would be as shown here, x2, and so forth. So, and here, Chapra is showing the truncation error, which basically is multiplied by h to the 5th. That would be the upper bound minus the lower limit, b minus a over the number of what is n, okay, in that particular case. In this case, for Simpson one-third, we know that n is equal to, so that's fixed. Now, if we want to apply for other values of n, like for example, when Simpson one-third rule is used to create the multiple application of the one-third rule, then you end up by what is known as Simpson composite for the one-third rule, and that will generate a truncation error as shown here. Now, the interesting part is that now the factor that is showing here, that is go to the average of the fourth derivative instead of the average of the second derivative. So definitely Simpson composite is a lot better than the trapezoidal rule.
We interrupt this program to bring you a special report.
All right. This is very important that I explain this, so I kind of did a parenthesis on this video just to ensure people understand this issue about the fourth derivative of for the truncation error when you apply, let's say, for one-third Simpson or Simpson composite as shown on this truncation error. Let's say that you are integrating a polynomial over the 3 as shown here, x to the 3 plus 1. You can pick any of that. Now, since you need to take the fourth derivative here as shown here, let's say that we start here taking the first derivative of this function. That will be 3x squared. Now, the second derivative of that function will be 6x. And now when you get to the third derivative, that's just 6. And eventually, when you get and try to get the fourth derivative, there's nothing, because the derivative of that, of 6, which is a constant, is 0. So but what I'm saying is that if you want to use Simpson composite or even Simpson one-third, the solution of this problem will be exact. All right? Like, for example, let's do a test. Let's say that I'm integrating this from 0 to 3, and let's figure it out by analytical method. Analytical method would be x to the 4 divided by 4 plus x, and that evaluated between 0 and 3, so that would be 3 to the 4 divided by 4 time plus 4, time plus 3, and so that would be that part. And when it's 0 minus 0, there's nothing there. So basically, you have 3 to the 4 that's 81 divided by 4 plus 3. Let's see what that result will be. That result is 23.25, and that's the analytical solution. So let's do Simpson 1/3. Simpson 1/3, the area under Simpson 1/3, that will be delta x over 3 times f of a plus 4 times f of b. F of a plus b divided by 2, this is a parenthesis, plus f of b, close the parenthesis. So our result will be delta x, obviously 3, delta x on this case will be b, I can write it here just so people follow what I'm saying, b minus a over n. For Simpson 1/3, that would be n is 2, so that's 3 minus 0 over 2. So we have 1.5. All right, so doing this part here, for my area under the curve will be 1.5 divided by 3 multiplied by f of a. What is f of a? That would be evaluating this function, this function on 0. So f of a, that would be 1 plus 4 times the function evaluated in 1.5. So let's evaluate the function in 1.5. So that would be 1.5 to the cube plus 1. So that would be 4.375, and now plus f of b, but f of b will be my function evaluated now when I'm right here at 3. That's 3 times 3 times 3, that would be 27 plus 1, that would be 28. So at the end, I have here, let's write everything down and let's add it together. So that would be 28 plus, that would be there. So I have here 1.5 divided by 3, that would be 29 plus 17.5. So our result will be, that would be 46.5 multiplied by 1.5 divided by 3. And let's see what we get. So that would be 3.25. Obviously, the exact result, because there's no a fourth derivative on the function. If the fourth derivative is available, then there will be a truncation error. That kind of finished this announcement, so now we go back to our regular program. So with that said, let's apply a little bit of this Simpson truncation error, and let's find out how would you do that. For today, I pick a kind of, I would say, easy to do analytically, hard to do all these derivatives that are required. Like, for example, let's say that I want to integrate a function like this. Let's say dx 1 plus ex. The analytical integration of that is shown by many other YouTubers, and by doing changing of variables and so forth, using perhaps partial fractions and many other techniques. And the analytical solution for that or the result will be something like this: 0. Let's say 64455. All right. So, and that's the analytical solution. Perfect. Now, let's say that I want to integrate this because I don't want to bother with the analytical solution, and I want to integrate this using Simpson rule. Either could be the application of a single step on of n equal 2 for Simpson 1/3, or an application which require n above 2. That would be 4, 6, 8, an even number. And for the application of the Simpson composite must be an even number. That's very important. Anyway, so the question is how I find, or how I can find the value of n for my application. All right. So the first thing that you have to do is define what will be your allow error, or your estimation of the truncation error. What would that be? So let's say that I want to be as accurate as this I would say, in the first 3 decimal places. So that requires that my approximate truncation error be something like this: 0.00, the first 3, that would be a 0 here, and then something else. Like, for example, I would say that, well, let's write it down. So I got 3 0 and a 1. So our solution, our numerical solution, should be as good as within the first 3 decimal places, will be identical like one as shown here on the first 3 decimal places. So with that said, what I need to do is this result shown here. Let me copy this. That result shown here, let me expand it a little bit more. That result shown there, and let's say that I'm talking about the absolute value, because that's basically what it is, must be less than or equal than the approximate truncation error that I'm showing here. That's it. All right, this is a 1. Given that I'm talking about the absolute value of this negative here, just you don't care anymore about it. So that's it. So the idea is, if I know the limit of my integration, b and a, I know those. 0 is a and b is 3. Now, I need to know also what is this? What is this average of the 4 derivative? Well, if you check Chapra's book, you will find that that average is basically the integration of the 4th derivative within the limit. In this case, let me put this better. It looks kind of ugly. Let me write it like this. So it's the 4th derivative of the function x dx over 3 minus 0. So one step further on this, it means if you integrate the 4th derivative, you know that you will end up in the 3rd derivative, right? And that 3rd derivative of x need to be evaluated between the limit 0 and 3 divided by 3. So in essence, I don't need the 4th derivative. I only need the 3rd derivative to do an evaluation between the limits, and that will be it. That will provide, let me fix this, look kind of weird. So basically, this 4th derivative, the average of the 4th derivative is just the evaluation of the 3rd. Let me write this like a number, because this tends to confuse people. Let's see. So it's just the 3rd, it's not f to the 3, please. Don't get confused. It's f, is the 3rd derivative of f, all right? And this is the 4th derivative of f of x. And this is the 3rd derivative. But it's not, what I'm saying is this integration of the fourth derivative becomes the third derivative, and that's it. So you just need to evaluate the third derivative of the function. Now, it's easy to say, hard to get it done, because now we're talking which is the function. In this case, my function is f of x is 1 over 1 plus e to the x. So how I get this third derivative? Well, let's start easy. We start always, saying that this is as simple as 1 plus e to the x to the minus 1. So this first derivative should be straightforward. Should be minus 1 over 1 plus ex to the minus 1, that would be 2 down here. But then this ex, the derivative of the inside one is 0, but ex is just ex. And then there, now you get the first derivative of our function. But remember, we need to get to the third derivative. So 2 more steps to get there. So how are you going to do that? Well, again, you can certainly do this like this. And let's see. We can apply a little bit of chain rule here. Let's write this like this. Is ex times 1 plus ex minus 2, and there's a negative here. So if we apply a little bit of chain rule into this, the result, the second derivative will be, like for example, let's derive the second time the first. So that will be a minus 2 minus minus, that will be a plus 2, and then we end up here with this part 1 plus ex to the third power, and then the derivative of ex is ex, but remember you have an ex here, so you just put it there, and that's it. That's the first part. And now let's move to the second part. So the second part will be this is a minus here, just write it down. So the second part, you will leave this alone. So it's 1 plus e to the x minus 2 times the derivative of ex, which happen to be ex. All right. If you do a massage a little bit that second derivative, should I do all the steps, or I'm thinking about it? I have the result. I mean, I just did a few minutes ago. I'm thinking whether I write all the steps. Let me write all the steps so I don't get nobody kind of confused here. So basically, this step end up the way it is. There's no problem there. So it's going to be 2 ex. In fact, I will leave this the way it is. Ex 1 plus ex to the third power minus, and here ex over 1 plus ex to the second power. All right. So what you could do is use a common denominator, and that will be 1 plus ex to the third power, and then you simplify this by having 2 ex minus, and here ex time one of these, 1 plus ex, and that will do. A little bit of more simplification on that second derivative will be, listen, here you have these 2 ex, and here you will show another one, ex, but it's a negative. So you will end up by having basically, let me put it this way, that will be ex times ex, and now you have this minus ex, so that will be minus ex over 1 plus ex to the third power. Finally, you can leave it like this, make life easier. So you can take, for example, a factor, one of those ex, and you end up by having ex minus 1 over 1 plus ex to the third power. And that will do. No more than that. I mean, that's as easy as I can get. Certainly, you can get this to this, and you can say, hey, this is e2x minus ex. You can do that, 1 plus ex to the third power. And that will do as well. So that's the second derivative. Now we need another step, the last one, which is the third derivative. For the third derivative, I'm going to introduce something that is called the quotient rules. I hope I pronounced that right. Quotient rule. In good Spanish might sound like la regla del cociente. La regla del cociente. The quotient rule. Quotient rule means when you are going to take a derivative of something, of a function. And let's say that this is the function that we are talking now, that we need to take the derivative of that. So the quotient rule is nothing else. Let's write the word. Let's see. Quotient rule. There we do. The quotient rule. All right. So will that do for you? It's sort of like the chain rule, but applied to when you have, you know, a function that in the denominator, and that will make life easier. Like for example, if you have f over g such that you want the prime or the derivative of a function that that can be split in two parts, like an f part and a g part, then you have the derivative of the first one times the second, but here's the chain, minus derivative of the second. Let's write this. So you leave the first one right times the derivative of the second, and here is the interesting part. All that divided by the derivative of the denominator square. See, that's how you apply the quotient rule. I mean, you cannot certainly apply the chain rule to this here. You can apply the chain rule here as well, because you take this part here and it go up to the -3, and then you have back again, sort of like a chain rule application. But for once, I'm gonna apply this quotient rule. And that's a bit quick sample. This is I'm dropping here through a tangent, but a quick sample. It cannot get easier than this. Let's say that I want the derivative with respect to x of, let's say, x2 over x3. Everybody knows that if I apply the derivative of x2 over x3, I better simplify this a little bit better, right? And that will be the derivative, obviously, with respect to x, than 1 over x, and the derivative of 1 over x, everybody knows that will be negative 1 over x squared. All right. No problem there. How about if we apply this? I mean, this is trivial case. Obviously, I mean, you would say you would never dare to use quotient rule just to do this kind of problem. However, I'm only explaining what's the story behind the quotient rule. So let's do that. Let's say, what is f? Well, f here is x squared. Obviously, g is x to the cube. So if I apply now this concept of f g prime, what I'm saying is f prime. What is f prime? Well, f prime is 2x and times g. But what is g? X to the cube. All right. Minus f. What is f? X squared times g prime. That would be 3x squared. And all that divided by g squared. That would be x to the 6. Now let's simplify what happened here. So you got, this is x to the 4, and this is, okay, so you got here 2x x to the 4 minus 3x to the 4 over x to the 6. If we subtract 2 minus 3, that will be minus x to the 4 over x to the 6, and voila, we get the same result, minus 1x over 2, just by applying what is called the quotient rule. All right, no big deal, sort of like a chain rule, kind of beef it up a little bit more for when you have something in the denominator. So let's apply the quotient rule for getting my third derivative here, and let's see if that makes life easy. That would be like this. So I can certainly, well, let's do this. Let's define what is f. F for me will be e to x minus ex, and let's define the g. G will be 1 plus ex to the 3. So if I apply the quotient rule, which is basically my third derivative, that will be the derivative of the first one. That's easy. That will be e to the 2x times the derivative of 2x. That will be a 2. So that will do. But then we have the derivative of this. That will be minus ex. And all that need to be multiplied by what is called g. In this case, g is 1 plus ex to the third power. Now, we move to the next part, which is f times g. So that will be minus f, which is e to x minus ex, close the bracket or parenthesis, and times g prime. But what is g? G is all this. So g prime will be 3 times 1 plus ex, that will be 3 minus 1, that will be 2, times the derivative of the inside, that this is the derivative of 1 is 0, ex. So I got with ex, and all of that has to be divided by g squared. This is g, so that would be 1 plus ex to the 3 times 2 to the 6th power. Talking about, I think obviously you will get to the point that doing this integration analytically might be easier, a lot easier than doing all this derivative. But not, the idea is, we are entertaining, and we don't pick a simple one. We pick a heavy duty one because the derivative are kind of complicated. But anyway, we got here. That's good enough for, I got the third derivative. The only thing that I need to do, if I can simplify it, oh, definitely. Or I can do, leave it the way it is, get to Excel and do the evaluation, because I just need for my average, and this is the interesting part, for the average. So for the average, what we need to do here, the fourth average of my fourth derivative, that's an average there, is equal to all of these, which is basically the third derivative. Let's call all this part big F. So that means F evaluated between the limits 0 and 3, 3 minus 0. And that's how you will calculate then the average of the fourth derivative. It's just going to the third derivative. But how sometimes we are like this, like we need to simplify. So this is kind of complicated. So check if your final result will look something like this for the simplification. So that third derivative, when you do a little gymnastic and with this, all that stuff there, will do something like this. Ex will be sort of like a factor, and you will end up with, I believe, 4 ex minus e to x minus 1, and all that divided by 1 plus ex to the 4th power. And you certainly see this coming, this 1 ex to the 4th power. So anyway, and it's coming from here. You see this is to the 3 and this is to the 2. So you can take a factor out of 1 plus ex outside, which cancel with the 6 that you have here. You end up with a 4 there. So it's not a big deal. So but the important issue here is that now that I have simplified my third derivative, the average that I'm looking is basically taking this function and do an evaluation between, if you allow me to do that, right? It's just the average of the fourth derivative is equal to the well, yeah, I don't have to write the integral anymore, because I know that the average is the integral. But what is the integral? This one here. That's it. So what I need to do is, you allow me to do that, is copy all this, put it here, and do an evaluation between 0 and 3 and 3 minus 0, and that will be, if you allow me to correct this, which is a little bit weird where it's located, it should be here. And that's it. So let's do one couple of things. Let's see if I need something else. We are pretty much ready to apply Simpson composite here, because that's basically what I'm doing, applying one of these. I can certainly apply Simpson 1/3, but let's apply this one. Let's see what the n come out. What would be the value, a proper value of n, just to do the first 3 decimal places exact as the analytical result, and let's find out whether that n is something small or big, right? So, and I think we don't need anything else except go to Excel and do this little bit of math here and come out with that average. So when I have that average, now that I have that, let me do a little bit more of gymnastic here, and let's take this here and I'm gonna open a new page. All right, so I'm right there, and what I really want is to get the n value. So the n value will be basically, if you multiply by n to the 4 to both sides, I end up with 1 over 180 b minus a. Actually, I can put the numbers. Let's write the number. 3 minus 0 to the 5th. Now, the only thing that I need is this. I'm going to leave it like that. So I need that average value of the fourth derivative, and all that need to be divided by 0.0001, right? Absolute value, I will keep it, less than equal n to the 4. So basically n to the 4, or n, will be 3 to the 5th over 180 over 0.0001, and the average of the fourth derivative, and all that has to be 1 over 4. Okay, and that will do. So this is how I'm gonna get my n value, as after I get first, or this value here, the average of the fourth derivative, and that will do. So what I need is let me plug all this in Excel. So I need, first of all, let me move again from one page to another here for 1 second, and let me grab all that. I need all this to go to Excel. Let's see if I'm gonna go to Excel, and you will see in a second. Hold it there for a while. Oh well, here we are back again, and we are in Excel, and I need to get the average of the four derivative, which is shown here finally, and let's do that. Actually, let's say this is what I'm evaluating, and this is the f of x, or it's not really f of x, it's just this function here. I'm gonna write it like this just for make life easier. Like for example, when it's 0, and definitely when it's 3. All right. So let's put the formula here the way it's shown here. That would be exponent of this. I'm gonna put everything. So leave Excel to do all the thinking. I'm just typing what I see here. So that would be 4 times. You can definitely simplify things around, but I'm not in the mood to do that. So basically, let Excel do it. See, anytime it's x, that's evaluating this value here, and so that's 4, and that would be minus, close this one, minus, that would be exponent of this guy, but now that guy is 2 times this guy here. Close that one up, and finally minus 1. All right, and let's see where we are here. I can certainly put there's a bracket here. Let's put that parenthesis right here. So that would be that parenthesis. It's not really required, but for the sake of the argument, keep the whole thing clean. And all that divided by, now this is parenthesis that I definitely need, 1 plus exponent of, in this case, of this guy here. Close that parenthesis, close the other one, and all that need to be elevated to the 4th power, and that will do. Let's see, any parentheses missing? Let's say just for the time being, and let's double check the parentheses. Yeah, I think it was the first one. The first parenthesis was not, as I said, it was not required. In fact, I can take it out because it's not really required. All right. Excel is quite intelligent to know what I'm doing. So it's the first one, which is this one, times, now the other parenthesis is very important. So because there's a subtraction here, there's a, we are taking that part out. That's a negative, that's a negative. That closing the parenthesis there, and all that divided by all this. Yeah, that would do. That's perfect. So the result would not change. All right, and that was evaluated at 0. How about evaluated at 3? That's simple. Just take this guy out, push it down, and that will do. So now what I have to do is get the equal. The result here will be this one minus this one, and all that divided by 3, and that will do. And that's the average. Let me rectify that average again. That's this value evaluated at 3 minus this value, which is evaluated at 0, and that end up with that value. And this is the average. So I got the average. Remember, absolute value all the way. In whatever we do here is absolute value. I don't care about the negative value. All right, so let's come up with n. Let's write here n equal. Let's open a parenthesis here. That would be 3 elevated to the 5th power divided by 180 divided by that small number 0.001. Nope, missing a 0. There we go. And all that then need to be multiplied by the absolute value of this guy here. Yeah, I missing the parenthesis. Absolute value of this guy, close there. Now I have this parenthesis here missing another parenthesis, and that will do. and all that need to be elevated to the 1 over 4. There we go. That will do. And let's see what n looks like it. Wow, very small. Well, doing this evaluation, the average value here, it never got any big at all. So that definitely, I saw that coming. And so remember, we are applying Simpson composite. That means n cannot be 5. N needs to be an even number. So the actual number will be n equal 6. And that will do. So let's apply n equals 6 and let's see what happens. Very simple. Let's apply Simpson rule right here. But this is Simpson rule composite. So there's some number multiplied by 2, other number multiplied by 4. Each one is very simple. You keep track of what we're going to be doing now. Like for example, let's say we know that A is 0, B is 3, and I said that it's going to be 6, and now dx or delta x is going to be b, let's put a parenthesis here, that's going to be b minus this guy divided by this guy. All right, so that's our dx. So now let's work this. X, the evaluation of the original function. Don't get confused with this fx. This fx was for this. The fx that I'm talking here is the function that we want to integrate. So, actually, let's do something for you guys here. Let's move this. Let me insert something. Choose cell right. All right. I think that was too much. I leave it here. Not that much. That would do. So get this off. All right. Here we're starting with obviously with the lower bound or the lower limit. That would be a. So the next one will be this one plus the delta x. That will be this one. Now remember, this delta x, since it's gonna be applied all over, then need to be fixed so that when I go here, it get to the. You see? Now here's the question. Be careful here. This is the first box. 1, 2, 3, 4, 5, and the 6th box right there. This identify as 1. That would require a 4. And the 1 identify as 2, which is even, that multiplied by 2. So let's do the fx here. And remember, the fx was 1 over parenthesis 1 plus the exponent of x, close that one, another parenthesis, and that will do. So let's come out with this to the end. Remember, we are applying Simpson composite. I can write that down, but let me apply it here first, and then we go with one note and we write it down in case you might have forgotten a little bit that expression of how it looks like. But it's very simple. The first one stay the way it is, so no changes here. Now this is the first one. That's odd. Odd need to be multiplied by 4, the function. So that means that this function here need to be multiplied by 4. Now this one here is a even. That means that the function needs to be multiplied by 2. Which is the function? This one. Multiplied by 2. Again, this is odd. Need to be multiplied the function by 4. This by 2. Finally, this one by 4. And this one stay the way it is. So what's the area? Well, the area should be the sum of everybody here. Okay, so let's write sum of all of them, and then multiply by, multiply by delta x divided by 3. Whew. Finally, 644 is the value that I'm getting. And let's say, how about, what is the truncation error? The true truncation error. Let's put it here. Actually, this is the area by the Simpson rule. Right now, let's write here the area, or the real area, or analytical result, as you want to call it. Let's write analytical result. The analytical result, if you remember, was 0.64455. All right. Now, here is where we can do the true truncation error. This is not an approximation. This is the real truncation error, because we know the exact solution of the integral, and that's the nice part of it. So the truncation error for this is basically the real number less than the Simpson composite application. Let's put this number in such a way that everybody will understand it better. Number, and let's open a little bit more. There we go. All right, so we get to 1, 2, 3. We asked for 3, and we end up with having a better resolution than what we asked. Well, the problem was, if you remember, let's see, the end value was 5. I either could use 4 or 6. I'd rather end up increasing the end value because I know that I'm going to get better resolution. If I use 4, obviously I will not get the resolution that I want. I leave that to you. Check that out. What will happen if instead of 5 I use 4? Since I use 6, I got very good resolution, even better of what I requested, because what I requested was 0.0001, and I got a lot less, which is great. I mean, it's good, but remember, that's because I went above for what was requested. It was 5. I cannot use 5. Simpson composite need to use even number. All right, be careful with that. It's not the same as trapezoidal rule. You can use anything for that value of n. No, I don't know. Should I have to say anything else? Let me write the formula that I use here, and we end this video right now. Let's see. Let's go to OneNote. The formula for Simpson, so we close this, is basically the area by the Simpson rule composite. Simpson rule composite will be dx over 3, and here will be f of a, but then we have times 2 times the sum of all even number. That would be 2, 4, 6 of f of x sub I, and that would be plus 4 to the sum of everything that is even. I mean, sorry, odd. So that would be 1, 3, 5, 7, blah, 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 plus f of b. And that's it. All this I consider is the stuff in the center of your sandwich. This is like a sandwich. This is one slice of bread, and this is the other slice of bread, and whatever is in the middle is either your cheese or your ham. Let's say that this is the cheese multiplied by 2 and the ham multiplied by 4, and that will do. So that's the end of this presentation. As I always said, be safe, whatever be your final destination. Bye.